All right, so we have gotten a couple little small introductions to the concept of torque, but in Unit 2, we said that forces cause acceleration, right? Force equals mass times acceleration. Well, in rotational motion, the same thing is true, except we're going to be a little bit more conscious about how we say this, because now for rotational motion, a torque causes angular acceleration, but it's not how much mass you have, and we've talked about this before, it's how your mass is distributed. So we're going to take a closer look at torque in this section. So, great conceptual example, stupid conceptual example, whatever you want to say. I have all these different forces here. I got force 1, force 2, force 3, and force 4, and they're all being applied on a door. And my question is, which one is the most effective at closing or opening the door? And that seems pretty obvious, right? First off, F2 isn't going to do anything for you. F3 it's not even going in the right direction, right? It is going to cause a little bit of rotation around the hinge, but what I'm really left with is F1 and F4. And if these two are identical forces, try pushing on a door right here, that close to the hinge versus right here, and this is going to be your best force. So forces have different effects on an object based on where and how the force is applied in comparison to the hinge. So torque is the rotational equivalent of force, and it's a really simple concept. It's just the radius or the distance away from the pivot point that you apply the force and the perpendicular component of the force. And what does that mean? It means that if I have, again, going back to my door, the circle represents a hinge. If I put my force like this or like this, I'm going to get two different angular accelerations, okay? The one that's straight perpendicular to the door is going to have the best effect. Now, radius, of course, is measured in meters. Force is measured in newtons. So torque, really simple, is just a Newton meter. So to really visualize torque, this is the best way, is to think about a wrench. An Allen wrench, a regular wrench, whatever. They all work on the concept of torque. Now, if I were to put a point at the rotation and extend a line out directly from the point of rotation, we call that the radial line. This is honestly not that important, but we'll talk about it as we define torque. Now, if I have my hand holding this wrench, sometimes, ideally, I would like to apply that torque right like this, but maybe my hand doesn't quite fit in right, so I have to apply it at some angle. So the angle that I apply it right now, it's measured in phi. You can measure it in theta. It really doesn't matter. But our book uses this notion that phi is this angle being applied right there. So ideally, it's perpendicular. Anything less than perpendicular, and some component of our force will be lost because it's not in the direction of the rotation. So I also, so what I'm talking about is that if it's not straight up and down, that's the perpendicular component, that's the parallel component. And the parallel component is just wasted force. Just like what we talked about work before. So torque is dependent on the perpendicular component to the rotation. There also is another way of examining this. It's the same kind of concept, is that I could look at the moment arm and the action arm. And the moment arm and the action arm is what we look at for what is that perpendicular component. It's the same concept. I will never refer to it as this, but it's just using sine cosine to evaluate the perpendicular component of the radius instead of the perpendicular component of the force. Either way, we end up with the same equation, that the tau is r perpendicular f, or r f perpendicular, and therefore the torque is rf sine phi, whatever that angle is here or whatever the angle is here, because those are going to be alternate interior angles according to geometry, and they have the same magnitude. So a huge application of this, and I'll have you guys take a look at it, and I'll do a quick little demo in class, is known as a cheater bar. Now, a cheater bar is when you put some type of bar or a pole around a wrench, same concept over here, to increase the length of that action, the length of that arm, to make it easier to apply a force. And technically what I said was just wrong. It's not easier to apply a force. It's just the further away you get with the force, the more effective your torque is, because you're increasing the radius that the torque is being applied. So we also have this concept of a torque wrench, and there's a little dialing calibration, but a torque wrench is a tool that's used to apply a specific amount of torque. So here's the head right here. There's this nice long action arm to help you get optimal torque, and then you calibrate it, and there's these little springs on the inside that once you get it to that torque or to the specific tension, it stops working. So then you know that it's torqued to the right. Typically you'll see it in foot-pounds, and you'll see that in like lug nuts of cars. You want to get them torqued to a certain foot-pounds of torque, and that's a great example of how we use torque. So here's a quick check. There's all these forces, which they're all the same strength. Which is the most effective? Of course, it's going to be F1. F2 is not going to do anything. F4 is difficult because it's closer to the door. We decrease our radius. And F3 is at an angle. So the effective force is less. Now, a torque tends to rotate the object, but we also have to think about, we had positive and negative forces, right? We can also have positive and negative torques. So a positive torque tries to rotate it counterclockwise because that is the positive direction. And then, of course, there's all these other random ones. Here's a negative torques, right? Here's other positive torques, right? It's just the direction and the effective angle or the effective force that's being applied. So here's an example. Ryan's trying to open a door. He pushes it with some radius, some degree, some force, and we can go through and figure out how much torque he's exerting. But we also say, how could he exert more torque? He'd either have to use more force or have a better angle on the door. And we'll go through this problem tomorrow and make sure the visual makes sense. Just like before, we had the sum of the forces in the x direction equals the net force, right? We can have that same thing with torques. We're not going to, okay? There's going to be a torque causing acceleration, but the same kind of concepts are true that we talked about with forces. So here's an example of pedals on a bike, right? You have 2 feet exerting forces, which are exert torques, and that's going to cause there to be a net torque. So some of the chains are gripped and pulled forward, some of the chains are pushed forward, right? It's a complex system. We have to look at all the torques involved. Again, we're not going to do it. So that was your quick little introduction into torques, and we'll talk more about torques causing angular acceleration in a future segment.